Hi all. In the previous video, we talked about the Claisen condensation. I think of it as an aldol reaction, but using esters instead of aldehydes and ketones. We can have variations of the Claisen, just like we did with the aldol. And here, let's do a intramolecular Claisen condensation, meaning that the reaction is going to be within itself. The enolate and the carbon it's going to attack is within the same molecule, intra. Now this does have a special name. It's also called the Dieckmann condensation, and it has all the ingredients that we've seen before, an ester and a base that matches the alkoxy group. Just like when doing an intramolecular aldol condensation, we want to identify the possible alpha hydrogens that we can remove. And on this diester, we have two alpha carbons, but the diester is symmetrical, so it actually doesn't matter which proton I remove out of these four. Let's say we make the enolate on this side of the molecule. That means we're going to make a connection between this alpha and this dot of the carbonyl. I just want to double check before we do the mechanism that this is going to end up being a 5 or 6 membered ring. Again, if you want to know more details about why we prefer 5 or 6 membered rings, or why they're most likely to form, you could go back to the aldol condensation, the intramolecular aldol condensation video. But if I do connect this alpha carbon with a dot, I have a ring that is 1, 2, 3, 4, 5 carbons. So that's the ring that we're going to make. And then again, if you use this alpha carbon and attack this dot, you would get the same product and the same 5-membered ring. Now, let me do the mechanism first, and we'll fill in the product up here based on the mechanism. And then I have a challenge, because now this diester is not symmetrical, plus I ask for the base and the solvent. Which one would you use? Let's look at this reaction first, the mechanism. And we have the diester here. Our base matches the alkoxy group, just in case what? Just in case we get exchange in transesterification. If we do that transesterification, it doesn't matter. We replace the alkoxy, the methoxy group, with another methoxy. But anyway, I did say we're going to use this alpha carbon on the left, so let's deprotonate that carbon. How do we do this? You make the double bond here, and you kick up the pi bond to the oxygen, because the enolate that I like my students to make initially is the oxygen anion enolate. It does have resonance, but for a mechanism where we head towards the final product, I don't typically ask for any resonance. I would ask for resonance if I wanted my students to comment on the stability of an anion, or possibly the acidity of different protons. We did create methanol. Okay, so what's happening here? I would definitely suggest always labeling your alpha carbon, because we have a double bond here, and when we remake this carbonyl and we take the pi bond and we attack the carbonyl on the other side, let me kick up this pi bond here. See, I drew the arrow in the middle of the pi bond. It doesn't really reflect which carbon, right, is being attacked to this dot. But we understand that we wouldn't attach that dot to this carbon of the double bond. We would attach it to the alpha carbon of the molecule. Okay, because this is the hydrogen that's that's the acidic. That's acidic. So let me double check this. Make that connection there. Yeah, that wouldn't make any sense. This carbon wouldn't have the right number of bonds if we connected the dot to this carbon also. Anyway, we have a 1, 2, 3, 4, 5-membered ring. My suggestion is, once you know the size of the ring, draw it right away and worry about the decoration on your bracelet next. Don't worry about it as you're trying to make the ring. So now that we have the bracelet, clasped, let's mark an alpha and let's mark a dot. I'll put the alpha actually here, and I'll put the dot here. It's arbitrary, but you know they have to be next to each other. That was the bond that was made. Now on this dot, we make the O-. We're doing mechanism. We still have the methoxy. On this alpha, we have another carbon. We remade the double bond. And we still have this methoxy group. Is it looking correct? Right, we made the bond between the alpha and the dot. Okay. What's next? We're going to remake the carbonyl and kick out the leaving group. Okay, this is looking good because I know my product from the previous video is a beta keto ester. Look what we have now. We have the ester right here. Okay, and we now have the keto group right here. We kicked out the methoxy or the alkoxy group. And that's important because we're going to use it right away. What are we going to use this for? We're going to use it to remove this alpha hydrogen. In the previous video where we first talked about the Claisen condensation, we mentioned that the alpha carbon that you plan to use to make the enolate, it has to have 2 protons on it. If not, then you will actually reverse the reaction. But because here we have a second alpha hydrogen, when we deprotonate it, and how do I want to do this? Very interesting. I am going to make the anion on this oxygen. Okay. It's the same mechanism that I showed in the previous video. We get this anion, and the anion is stable. And you can isolate the anion for protonation in the second step. But let me just finish this real quick. And we created CH3OH. Remember the rationale? This deprotonation is a strong driving force to push the reaction forward because the pKa of this is around 15.5. And it's actually it's actually the weaker acid because the ester ketone alpha carbon has a pKa around 11. The diester is 13. The diketone is 9. This will be halfway in between. That will be 11. Okay. But that's not our final product, right? Our final product has to be the beta keto ester. So we're going to protonate. And what we're protonating in the second reaction with H3O plus is we're protonating the alpha carbon. How do you want to show that? You remake the double bond, okay, and you protonate the alpha carbon. I feel there's a question out there, and the question is, we have an oxygen anion. Why don't we just make the OH group? Well, your choices are this. Either you keep the carbon-carbon double bond and you make this an OH, or you make this product where the double bond is between the carbon and the oxygen, and you put the proton on this carbon right here. The better choice is this one, because carbon-oxygen double bonds are stronger and more stable than carbon-carbon double bonds. So it's the idea of Sure, if you protonate this, you make the enol, but you know that in most cases the keto form is more stable than the enol. So you could do it a couple ways, right? You could protonate it now on this alpha carbon by doing these two, actually 3 mechanism arrows, and then you have the enol, which will isomerize to the keto, or you can directly make the keto form by drawing these 3 mechanism arrows. We created water, I think. Yep, water here. Okay, and it should be 5 steps. 1, 2, 3, 4, and then the 5th step is the protonation. Let me label everything and make sure that we have the right product. It is a beta-keto ester, which is what we expect. I think there's a space there. And let us draw now the product up here based on what we saw in the mechanism. Oh, actually what we see here, right? Basically, you are connecting the alpha to the dot and you're kicking out the leaving group. So here's my 5-membered ring. My alpha attacked the dot. The dot still has the carbonyl. In the final product, it will have the carbonyl. On that alpha, you have another carbon, and you have a ester group, like that. That is the same product I have drawn down here. And if you want to count carbons, you're going to lose these. We'll count from here. Let's use purple. 1, 2, 3, 4, 5, 6. And you do keep this methoxy group that does not leave. Starting from the dot, 1, 2, 3, 4, 5, 6, and your methyl of the methoxy is carbon number 7. Alright, and the last thing before we check out the second reaction is, just to remind yourself as you're studying, you don't have to do this on the exam, but as you're studying, remind yourself that this is the bond that was made between the alpha and the dot. And you are making a beta keto ester. Now, this reaction here, we have a diester again, but it's not symmetrical. Our 2 alpha carbons are different. So if I make this side the enolate and attack the carbonyl here, I will get a different product than if I take this alpha carbon and attack the carbonyl over here. Both of them make, I think, a 6-membered ring. Whether we go here, 1, 2, 3, 4, 5, 6, or if we go here, again, go to the carbonyl, 6. But one of them is better than the other because remember that rule? When you do a Claisen condensation, the alpha carbon you use to make the enolate needs to have 2 protons, or else you won't be able to form the anion and you'll actually reverse from here. You'll reverse course. You want to trap the anion and you need that second proton to be able to be removed to make that anion and push the reaction forward because you are making the weaker acid. Understood? So it's this alpha carbon that has the 2 hydrogens. This one only has the 1. So we are rejecting making the enolate on the right, and we're not doing this ring closing, we're doing the one on the bottom. Now, I'm getting a little bit confused. There's a lot of markings. I know we have a 6-membered ring. Let me draw that right away. And I know in that 6-membered ring, it's always going to be an alpha connected to a dot. The alpha I'm using, oh boy, is this one. And the dot I'm attacking is this one. I am losing this leaving group. Okay. So there's my alpha, this one right here. And I have this ester hanging off of the ring. So here's my ester. It's a O-ethyl. I'll draw out the ethyl group like that. And then when that attacked this carbon, the leaving group left, And that carbon of the dot still has its carbonyl. So that's great. We have a beta keto ester. Right? This is the, if you recall, this is the beta now in the final product. That's not attached to the dot anymore, but this carbon here within the ring next to the dot has that methyl group, and we have that. Okay, that's your final product, I believe. We could count from the carbon we attacked. 1, 2 has the methyl. 3, 4, 5, 6, 7. 1, 2 has the methyl. 3, 4, 5, 6, 7. And then the O ethyl. Oh, they're asking for the type of base. We have to match the leaving group. So the base we could use is NaOET. And then the solvent will be ethanol. Ethanol is a liquid, right? And it is the conjugate acid of the OET base. We could draw it like this, HOET, right? But ethanol, you know, is this molecule. Okay, I think I'm good. You know, that is actually made because it is condensation. We are condensing liquid ethanol in this case by kicking out this OET minus, which eventually gets protonated just like here.